Have you ever tried to organize a massive, chaotic pile of books all at once? It is completely overwhelming. Instead of trying to tackle the whole mountain in a single sweep, there is a simpler approach. You split the pile in half, and then you split those halves again. You keep cutting the stacks down over and over until you are looking at just one single book. This strategy turns a giant sorting problem into a series of simple tasks, comparing just two small items at a time. In computer science, this is the core of divide and conquer. Let's see how a computer uses this strategy to organize a messy list of numbers: 8, 3, 5, 1, and 6. Looking at this digital array, the algorithm splits the group directly down the middle. One block gets 8 and 3, another gets 5, 1, and 6. The computer repeats the splitting process over and over, breaking them apart until every single number stands alone. By breaking the list down entirely, we reach a very helpful starting point. Because a single number cannot be out of order with itself, it is by definition already sorted. Now we begin the second half of the strategy, merging these isolated numbers back together by comparing them one by one. When we look at the 8 and the 3, the computer compares them to see which is smaller. The 3 drops down into a new block first, followed by the 8, forming a sorted pair. The algorithm performs the same comparison for the 1 and the 6. Since 1 is smaller, it takes the first spot, and the 6 follows. When a single number like the 5 meets a pair, the same logic applies. The 1 drops down, then the 5 slides into the middle, and the 6 finishes the group. Stitching together two small, already sorted lists is much faster for a computer than hunting through a randomized pile. That efficiency is what makes this entire process work. We are now left with two sorted halves, 3 and 8 on the left, and 1, 5, and 6 on the right. It is time for the final merge. In this diagram, you can see how the computer uses markers to track its place. Because both halves are already ordered, it only needs to look at the very first number in each group, the 3 and the 1. 1 is smaller, so it snaps into the first empty slot below. The marker on the right moves to the 5. Now the computer compares the 3 and the 5. The 3 is smaller, so it takes the second slot. The left marker moves to the 8. 8 is compared to 5. 5 takes the next spot. 8 is compared to 6. 6 takes the next. Finally, the 8 falls into the last slot. The list is now perfectly organized. Looking at the process from above, you can trace the initial chaotic list splitting down into single branches, and then merging back together into a sorted whole. By combining relentless splitting with step-by-step merging, the algorithm guarantees a perfectly organized result without ever being overwhelmed by the scale of the data. There are dozens of ways to sort data, but programmers rely on this specific method for its reliability. This reliability is measured by time complexity, which for this algorithm is written as O(n) log n. This is essentially a guarantee of consistent, predictable speed. Whether a list is already sorted, completely random, or even perfectly backward, the progress bars all complete at the exact same time. The speed remains the same regardless of how messy the data is. This guaranteed speed does have a cost, however. It requires extra digital resources, a factor called space complexity. As this animation shows, the computer cannot swap the items within their original slots. It needs a secondary, temporary staging area to hold the numbers while it performs the merges. This is the central trade-off of the algorithm. You use more of your system's memory to ensure that the sorting happens at maximum consistent speed. This trade-off is ideal for handling massive streams of data. When a dataset is too large to fit into a computer's standard memory, this method breaks it into manageable pieces that can be processed in parallel. It also provides an advantage called stability. This means that if two items in a list are identical, they will stay in their original relative order even after the sort is finished. Because of that precision and reliability, this method, merge sort, is the standard choice for the internal sorting tools in major languages like Java and Python. Merge sort handles overwhelming chaos by dividing the problem down until each piece is small enough to conquer.